Hi student, in today's session for electrochemistry, I will discuss electrochemical cell. The next section of this chapter, electrochemical cells. Electrochemical cell is a device that converts chemical energy to electrical energy. In previous section, we discussed electrolytic cell. Electrolysis, we discussed electrolysis, and the process of electrolysis takes place in electrolytic cell. Electrolytic cell basically converts electrical energy to chemical energy. Means a chemical reaction takes place on passing electric current. While in electrochemical cell, chemical energy is converted to the electrical energy. Means chemical energy of a spontaneous reaction change to electrical energy. So remember that electrochemical cell is a device that converts chemical energy to electrical energy. Every electrochemical cell is made up of two half cells. In an electrochemical cell, there are two half cells. One is called as anode half cell and another is called as cathode half cell. In an electrochemical cell, there are two half cells. The first is anode half cell and second is cathode half cell. Now, in a half cell, there are two types of conductors. One is metallic conductor or electronic conductor. Each half cell contains a metallic conductor or electronic conductor and electrolytic conductor. Half cell is made up of a metallic conductor and electrolytic conductor. Metallic conductor is a wire or plate of metal, a wire or a plate of metal, a rod of metal, while electrolytic conductor is solution of electrolyte, and that electrolyte can be acid, base and salt. Electrolyte can be acid, base and salt. These acid, base and salt can be taken in solid form or in their molten form. It depends on the nature of electrochemical cell. So every half cell is made up of two conductors. One is metallic conductor and other is electrolytic conductor. On the basis of these two type of conductors, half cells are of the following types. Types of half cells. There are the following types of half cells. The first is metal ion, metal ion electrode or half cell. Metal ion electrode. Half cell is also termed as an electrode. In metal ion electrode, there is a rod of metal dipped in solution of this metal ion. For example, a copper rod dipped in a solution of copper ion. So let's say this is the solution of copper ion and this is copper rod. So this particular half cell is called as metal ion half cell, and this metal ion half cell can be represented as metal and corresponding metal ion in aqueous form. This is the representation of this half cell. Metal ion half cell can act as anode of any electrochemical cell, or cathode of any electrochemical cell. So can act as anode as well as cathode. Now, if it acts as an anode, then the corresponding electrode reaction is metal will get oxidized to corresponding metal ion with loss of electron, because at anode the process of oxidation will take place. If it acts as cathode, then process of reduction will take place, and it is the metal ion that will get reduced to metal. So Mx plus in aqueous form plus X mole of electron to form M in solid form. And remember that process of reduction occur on cathode. In electrochemical cell, the polarity of anode anode is negative electrode and cathode is positive electrode. Remember that the polarity of anode and cathode in electrochemical cell and in electrolytic cells are different. Polarity of these two electrodes in electrochemical cell and in electrolytic cells are different. In electrochemical cell, anode has negative polarity. Because of the occurrence of a spontaneous chemical reaction in the cell. And when there is an oxidation process at anode, it gives out some electron. So anode will have plenty of electrons, so it will require the charge of these electrons. So that's why it will become negative electrode. In electrochemical cell, anode is negative electrode and cathode is positive electrode. While in electrolytic cell, anode is positive electrode and cathode is negative electrode. So remember, in electrochemical cell, these are the correct polarity. So metal ion electrode can act as a cathode as well as anode. We can see various examples like zinc electrode, so zinc electrode is a rod of zinc dipped in a solution of zinc sulfate. We can take any soluble zinc salt copper electrode. We can use solid copper in copper sulfate solution. Silver electrode, Az solid in silver nitrate solution. So this is the metal ion electrode. First category. Now second category is gas. Gas ion electrode. In gas ion electrode, a sheet of inert metal is taken. You can say platinum. Over in a closed chamber, a sheet of platinum is taken in a closed chamber, closed glass tube you can say, and dipped, and from here we can pass a gas. And here we have taken a solution having gas ion. For example, hydrogen gas is passed over platinum, and here we have taken an H plus ion solution. So this representation is for gas ion electrode. So this gas ion electron symbolically can be represented as platinum having any adsorbed gas over the surface of platinum, and that is in contact with corresponding gas ion that may be in cationic form or that may be in anionic form. So Pt in solid form, Y2 in gas form, and Y minus in aqueous form. Depending on the nature of gas, its gas ion can be cationic in nature or it can be anionic in nature that can exist in aqueous solution. So here we need an inert metallic conductor over which the gas molecules will get adsorbed. These gas ion electrode again can act as cathode as well as anode. So suppose this is gas ion electrode, and if it acts as an anode, then process of oxidation will take place. So this gas will get oxidized to gas ion. The electrode reaction have only those chemical species which are present in the half cell. All the species that appear in half cell may participate in electrode reactions. Some of them may not participate. But any extra species you cannot consider. So it is the gas that will get oxidized to gas ion. So X2 in gas form on oxidation form 2X plus in aqueous form plus 2 electron. This will be the corresponding half cell reaction if this electrode acts as an anode of any electrochemical cell. Now if it acts as a cathode, then this reaction will get reversed. So 2X plus in aqueous form plus 2 electron to form X2 in gas form. Similarly, if we have Pt in solid form, Y2 in gas form and Y minus in aqueous form, then in this type of gas ion half cell, the corresponding reactions are, if it acts as an anode of any electrochemical cell, then process of oxidation will occur in this half cell, and during oxidation process gas ion will get oxidized to gas. So 2Y minus in aqueous form from Y2 in gas form plus 2 electrons. If it is used as cathode of any electrochemical cell, then process of reduction will occur on cathode or in this half cell, and during reduction gas will get reduced to gas ion. So Y2 in gas form plus 2 electron form 2Y minus in aqueous form. Now the same reaction will get reversed depending on the nature of these half cells as anode and cathode. So these half cells can act as anode as well as cathode. Now we can take some example like hydrogen electrode. In hydrogen electrode, hydrogen gas at some pressure is passed over platinum and dipped in an solution of H plus ion having some concentration, and let pressure of hydrogen gas is P atmosphere and concentration of H plus ion is some X molar concentration. So this is the hydrogen electrode, and in hydrogen electrode we also have standard hydrogen electrode, sheet. Standard hydrogen electrode is hydrogen electrode in which hydrogen gas is passed over platinum at 1 atmospheric pressure and dipped in a solution of H plus ion of 1 molar concentration. The standard reduction potential of this half cell is taken as 0.0 volt. It is just assumed value to measure the potentials of other half cells. The standard reduction potential of standard hydrogen electrode is assumed as 0.0 volt. It is just assumed value. Actually, it is not 0.0 volt. It is an assumed value to measure the standard potentials of other half cells. So this is the hydrogen electrode. We can consider chlorine electrode. In chlorine electrode, chlorine gas is passed over platinum and dipped in a solution of chloride ion having some concentration. If we consider oxygen electrode, platinum in solid form, O2 gas at some pressure P atmosphere and hydroxide ion in aqueous form at X molar concentration. In fuel cells, hydrogen electrode and oxygen electrodes are used. In fuel cell, anode is hydrogen electrode and cathode is oxygen electrode. Cathode is oxygen electrode. So, this is the second category of half cells, gas ion electrode. Next we can consider metal insoluble salt anion electrode. So third half cell is metal insoluble salt anion electrode. In this type of half cell, here we can say this is the metal rod. Let's say a suitable metal M, over which a paste of insoluble salt of this metal is placed. Let's say insoluble salt of this metal be Mx, insoluble salt of this metal, and this entire arrangement is present in a solution of salt, in a solution of anion of this salt. So this is metal. This is metal, a coating of metal insoluble salt. And this is the salt anion solution. So it can be represented as metal, metal insoluble salt, and salt anion. These half cells, these type of half cells can act as again as cathode as well as anode of any electrochemical cell. So suppose these half cells act as anode, then corresponding reaction is oxidation reaction. So now it is the metal that will get oxidized to insoluble metal salt. Metal will get oxidized to insoluble metal salt. So M in solid form plus X minus in aqueous form to form Mx in solid form plus electron. The corresponding electrode reaction must involve only those chemical species which are present in half cells. We can't change, we can't introduce extra species. Now if it acts as cathode, then this reaction will get reversed. So insoluble metal salt will get reduced to metal. We can consider two important examples for this category. It is AgCl, and KCl. We can also consider Hg in liquid form, Hg2Cl2 in solid form, and KCl in aqueous form. This electrode is called as calomel electrode. It is called as calomel electrode. And this calomel electrode can be used as secondary reference electrode. Can be used as secondary reference electrode. So these are the two important metal insoluble salt anion electrode. Metal insoluble salt anion electrode. The fourth category is redox electrode. In redox electrode, the same chemical species is present in two different oxidation states. So, suppose this is again an inert material and present in a solution having solution of metal or any species in X plus state as well as in Y plus state. The same substance should present in two different oxidation states. the mixture of substance in two different oxidation states. Either X can be greater than Y or Y can be greater than X depending on the nature of M. So this electrode can be represented as platinum in solid form, Mx plus in aqueous form, and My plus in aqueous form. Now this vertical line represents phase boundaries, phase separation. So here there is only one phase boundary, this platinum and this solution. Here there is a phase boundary. These two are only in two different states, two different physical states. These two substances are in same physical state, so there should not be any phase boundary. These two will be separated by comma. So the solution, electrolytes present in same solution should be separated by comma. And for different phase boundaries, we have to consider the vertical line. If it acts as an anode or cathode, let's say X is greater than Y, suppose. And if it acts as anode for any electrochemical cell, then the process of oxidation will take place. So Y will get oxidized to X. My plus will get oxidized to Mx plus. So My plus in aqueous form on oxidation form Mx plus in aqueous form plus X minus Y electrons. If it acts as cathode, then process of reduction will occur on cathode. So the same reaction will get reversed. So Mx plus in aqueous form plus X minus times of electron, X minus Y times of electron to form My plus in aqueous form. My plus in aqueous form. Here there are two important examples for this type of electrode. Platinum in solid form having a solution of ferrous ion and ferric ion. Okay. Platinum in solid form QH2 and Q. QH2 and Q. Q stand for quinhydron. Q stand for quinhydron. Quinhydron is this chemical substance. So it is Q. So the corresponding electrode reaction that will take place is of this type. So this quinhydron electrode is an important category. Quinhydron electrode. So these are the various types of half cells. Now when we connect these two half cells, a cell will form, a cell will be constructed, but the cell obtained just by connecting two half cells may be functional or may not be. Now, if various half cells are given and you have to select any one of them as anode and another one as cathode, then we will use half cell having highest value of standard reduction potential half cell having highest value of standard reduction potential can be used as cathode and half cell having lowest value of standard reduction potential can be used as anode to construct an electrochemical cell. Instead of lowest value of standard reduction potential, we can use highest value of standard oxidation potential. So highest value of standard reduction potential for cathode and lowest value of standard reduction potential as anode. So this is the criteria. So all half cells are arranged in the order of their value of standard reduction potential, and the series in which all half cells are arranged in decreasing order of the values of their standard reduction potential is called as electrochemical series. And from this series we can identify the corresponding values of standard potentials. The potential associated with reduction reaction at an electrode is called as reduction potential, and potential associated with oxidation reaction is called as oxidation potential. And if these potentials are measured under standard condition of reactions, and we call these potentials as standard reduction potential and standard oxidation potential. Standard reduction potential and standard oxidation potentials. So suppose we have a zinc electrode with value of its reduction potential as minus 0.76 volt, and a copper electrode with standard reduction potential as plus 0.34 volt. So these are their corresponding standard reduction potentials. This not indicate 0 as a power indicate, standard, and this is the reduction process, Zn2 plus getting to Zn, getting reduced to zinc. So it is a standard reduction potential. This is also standard reduction potential. So here the zinc electrode will use as anode because this is the lowest value of standard reduction potential, and copper electrode is used as cathode. So this will be used as anode and this will be used as cathode to construct a electrochemical cell. So here we will take a zinc electrode in which a zinc rod is dipped in a zinc sulfate solution, while in another electrode a copper rod is dipped in a copper sulfate solution. So these two are the corresponding half cells, and these two can be connected to an ammeter to identify whether there is a flow of current or not. Now here this zinc is anode and copper electrode is cathode. So polarity of this anode is negative and that of cathode is positive. In electrochemical cell, anode is of negative polarity and cathode is of positive polarity. Now see what happened. At anode, the process of oxidation will take place. So it is the zinc ion, zinc that will get oxidized to zinc ion. So in solution, zinc ions are travel, an electron comes out, for the external circuit. Electrons will move to external circuit, and at cathode the process of reduction will take place. So copper ion present in solution will move towards cathode and zinc ion are coming in solution. Electron will enter in electrochemical cell through cathode and it leaves through anode. So by seeing the direction of flow of electron, we can identify the direction of flow of current. The current will flow from cathode to anode. Electrons are flowing from anode to cathode. So current will flow from cathode to anode. Now, before the oxidation process at anode, the solution was electrically neutral because the solution was made up of equal number of moles of zinc ion and sulfate ion, equal positive charge and equal negative charge. After some time, as soon as some zinc ions produced in this half cell, the solution will become positively charged. So no more zinc ion will be allowed in the solution because of the repulsion between positively charged solution and zinc ion coming to this solution. This is called as liquid junction potential. Similarly here, Before the reduction process of copper ion, this solution was completely electrically neutral because of presence of same number of moles of copper ion and sulfate ion. After some time, some of the copper ion will get reduced from this solution and will deposited as copper on this copper rod. And after some time period, this solution will become negatively charged. So in this negatively charged solution, further movement of electron will not take place, because again a liquid junction potential has developed between the solution and this copper rod. And here there is a liquid junction potential has developed between solution and zinc rod. To overcome this liquid junction potential, these two half cells are connected through inverted U-shaped tube having a gelatinous substance called as agar-agar. A gelatinous substance called as agar-agar having electrolytes. So this is called as salt bridge. So salt bridge is used to remove liquid junction potentials between metallic conductor and electrolytic conductor. The salt bridge contains KCl or KNO3. Now what happened when some of the zinc ions formed in anode half cell because of oxidation reaction, same number of anions also travel from salt bridge to anode compartment to make this solution electrically neutral. Similarly, when some of the copper ion get reduced at cathode because of the reduction process, some of the potassium ion will travel to the solution to make solution electrically neutral. So salt bridge is used to overcome liquid junction potential as well as to complete the internal circuit. So this is the criteria to construct an electrochemical cell, and this electrochemical cell can be represented as anode is written on left hand side and cathode is written on right hand side. Anode and cathode are separated by two parallel vertical lines that indicate the presence of salt bridge. So anode is zinc half cell and there is a salt bridge, and there is copper sulfate that is in contact with copper. So just this arrangement should be represented in this way in the order of their connectivity. So zinc, then there is a zinc sulfate, then there is a salt bridge, then there is a copper sulfate, and then there is a copper. The concentration of these electrolyte solution should be represented in parentheses. So this is C1 molar solution and this is C2 molar solution. So this is anode half cell, and this one is cathode half cell. And whatever is the potential of this cell should be represented on extreme right hand side of the cell notation. This is the cell notation. So these are the electrochemical cells. its half cells, criteria to decide anode and cathode, and cell notation, and the presence of salt trace. So it's all about today's lecture. In next lecture I will continue the same thing, that is notation and some more example of electrochemical cells. So you must revise it before coming to next lecture. It's all for today's lecture. Thank you.